is more important. So it has, the construction uses geometry. So we look at all polynomials of degree 2, and I assume that this polynomial has no real roots. Then I take all its multiples, it's an idea, and this idea sits in the ring of all polynomials. So this is an idea. It's an idea depending on those two numbers, so I say b, comma, c here. And then the amazing thing, of course, no real roots. So some condition about the discriminant, we have that the ring modulo this idea. And now comes something which is extremely difficult. Very few people know. So I do not say equal complex numbers. This is isomorphic to the field of complex numbers.
Okay.
When we take an idea of easier type x minus a, then I can write equal to real numbers. And the reason is, the real number, that field, has no self-symmetries. If you have a self-map of the real numbers, it is always identical. The self-map that preserves addition and multiplication is automatically identical. The space of self-maps of the complex numbers that preserve addition and multiplication is huge. Everybody knows two such self-maps, the identity and complex conjugation, but this is a very tiny piece. The space of self-maps of the field C is bigger than any set you know. If you know already, say, Banach space, you will say the Banach space is an infinite dimensional vector space, has many points. The automorphism of the field C is bigger. So do something. Here, circular symmetry is very good. So I write isomorphic as a field. So now we look at the space of all such ideas. And this space, so B and C varies. This space, this is our hyperbolic plane. As set. So I know the points, set. I do not know the geometry, I do not know the measurement. So I must tell you how we make, say, something called line. And this we did yesterday. If I take two such a polynomial, I make short, I write it as P index BC. So P index BC, I wish to have the name for every such polynomial. So the name is, I look at the complex root with positive imaginary part. So such a polynomial, the roots of this, there are two of them, and one of them sits in the upper half plane. That piece of the complex plane where the imaginary part is positive. So, such a polynomial gives me a point in the upper half plane. This is the real line. The y-board is the complex plane, and above this line, that is the upper half plane. So, if I have two of them, P index BC and P index B dash and C dash, then I wish to do geometry. And if I wish to do geometry, I must do a lot of things. For instance, one thing is I must know what is the shortest path. But before talking about the shortest path, I must say what is the metric and how do I measure angles, and the whole business of geometry. So we have to know this. So the first thing is, and that is something which you can figure out yourself. It is also in the notes, but this you only need to know the Pythagorean theorem you learned at high school. The following fact is true. I think the convex combination of those polynomials, the convex combination, you see the sum of the coefficients is 1. This is a linear combination. But I think the convex combination, I wish that t is positive, and I wish also that 1 minus t is positive. So in short, this means I wish that t is in the interval 0, 1. So if I do this, so a real polynomial of degree 2 without complex root, it's easy to say that are those which are positive all the time. So t is positive, this is positive all the time, this is positive, so the whole thing is positive for every t in this. So this family of polynomials gives me a family of ideals. Gives me a family of ideals. And this family of ideals, the way you see it in front of me, I look where is the 0 of this polynomial in the upper half plane. So this gives me a family of points in the upper half plane. And then the very important thing is, if you do Euclidean geometry, if you connect those two in Euclidean way, and you take the perpendicular to the midpoint of this connection, perpendicular in the Euclidean way, and you draw a circle. Is this a center? That arc of the circle, this or the ZTs. The ZTs travel along such an arc. This is a small computation, everybody knows. We have a formula for this square root. You know the formula to solve a polynomial of degree 2, square root somewhere and so on. Now, we can say, so we have this line of polynomials from 0 to 1. But now I do it follows. This is 0, this is 1, and here runs t. T runs here. But I can of course let t go outside. And I can let go t outside in the other direction. At some moment, this polynomial gets real roots. There's a point here and a point here, where the polynomial gets real roots. So this point, let's call it small n, b, c, b prime, c prime. This polynomial depends, this family of polynomial depends on 4 real numbers. And this I call capital M, b, c, b prime, c prime. So now we have the following thing. We have a line, and on this line we have 4 points. We have 0, we have 1, we have little m, and we have capital M. And I wish to make a measurement. Jose is not here.
He's preparing his lecture.
Yes, so I can say something better he does not hear. But you can tell him later. It seems that he does not like projective geometry. It seems. I will say why we need projective geometry. So if you look in the sky, you see sometimes objects, sun and some other things. And you are here and you look in the sky to objects. Imagine that the vectors which connect yourself with your object lie in a plane. So this gives 4 vectors in a plane. And what is if you measure, if you do astronomy? You you know very well the direction of this vector. You have such a building, this kind of building, you know which window you must open to see the thing you like. But you do not know the distance to that thing you like. This are stars, and you are watching from here. So what you do is, what you have is, you have 4 directions. If you wish to say 4 vectors, and you forgot how long they are. You can also say you have 4 lines. So if you have 3 points on a line, and you look at it, out of this you cannot make a number. Everybody knows, by taking photographs, that the size of the building, and you have to say the cathedral, here you have the door, you are here, you take a picture. Then certainly the door is half as big as the whole cathedral is high. And if you go further away, the door becomes smaller. So taking pictures does not tell you something about sizes. But if you have 4 points, out of this I can make a number. The number goes as follows. So we have this picture, I have 4 lines. Going through the point. And out of this I wish to make a number. This gives me an element, it gives me a number. How we do? First, we choose the horizon. We do this in our building. That's one option. The other option is you do it in infinity. So what we take is we take an extra line which does not go through this and cuts all the others. But the extra line could be at infinity. Then we give names. I call this line I call x and this line I call y. And this I call A and this I call B. Now we say A is the graph VH of a map from x to y. I prefer to put this line at infinity, and the picture is as follows. This is the x-axis, this is the y-axis, the horizon at infinity, and here we have an extra line A. How we make a map from x to y? We take a point here, we look to the horizon, so we look parallel to the x-axis, we hit the graph, and then we go parallel to the y-axis, and then we have a map. The same could be done here. And I go here, parallel to the x-axis, so I look there. Then I intersect here. Then what I do is, from here I look back. From here I look back. And then I'm here. So P goes to Q. This Q is A of P. I use the map, I get the same letter. That's the construction to what I did here. You look to the horizon, infinity. Then from the horizon you come back and you have the usual school way of making the graph map. So we have a map from x to y. I gave it already a name, the map from x to y. But at B, I can use it the same way as a map from y to x. Use the other line as graph. Then I can compose them. This is a map from x to x. This map is a fixed point. Let's call this point O. O is fixed. So now I get a number. I have a map from a line to a line and a fixed point on it. I can take the derivative at that point. At that point, I see how the scale is changed. So I take, if our maps are linear, that will be a linear map from x to y. So when everything is linear, which is the case when I put the horizon at infinity, then the map is a linear map. No need to take the derivative. I write it as a matrix and then I see one number. That is the number. And the number is called lambda. Lambda is the differential of this map at the point O. The amazing thing is, this number does not show depending on where we take the horizon. So therefore we can make measurement only from directions. This leads to projective geometry. If you know the vectors, and you know how long they are, no need for projective geometry. But each time you have vectors, and you do not know how long they are, and you know the direction, better you try to understand projective geometry. So now we have a measurement here. If you wish to have a quick formula, what you do is that you have 4 points on the line, and you want not to do this, but you wish to have a quick recipe, you take the two big distances. So that means if in this case, it is 1 minus m from here to there, and then the other big distance is m minus 0, and you divide by the two small distances. Small distance is 0 minus m, and the other is by m minus 1. That is the number on which we are talking. And this expression has a name. It is cross ratio, and I do not know the Spanish name.
Razón doble.
Huh?
Razón doble.
Huh?
Razón doble in Spanish.
Razón?
Razón doble.
The Germans also say double letters. They say. And this is a basic measurement. So when you know this, now I have a distance here. I have a distance, let's say the distance between those two polynomials. Distance in hyperbolic space between polynomial is a half logarithm of the cross ratio of those 4 points. And now appears something amazing. This geometry, so when I have distance, I can take distance squared and take the derivative of distance squared at every point. Then I get a quadratic form. That gives me a Riemannian metric. So we don't do this. This formula gives a Riemannian metric, gives the measurement of angles, and has many things in this geometry. So why do we need this geometry? Why do we need this geometry to understand Riemann surfaces? From this geometry, the first amazing thing is that you can make triangles with many angles which you cannot make in Euclidean geometry. In this geometry, if you draw a triangle, then because we have already a Riemannian metric, I do not know the details how to make a Riemannian metric out of this measurement. It's a Riemannian metric. Then what you have is that the sum of the angles is not pi, but it's less than pi. And you can make triangles of any size, measured with angles, as long as you follow the following constraint. All angles are positive, and the sum of the angles is less than 1. For every such triple, you have a triangle. From this follows the following. You can make polygons such that the sum of, with many sides, with 4 G sides, this is perhaps not 4, 1, 2, 3, 4, a side missing, but that's not so important. You can make polygons with 4 G sides, and you are free to choose the angles. But I did like this, and it watched to you, not to the white water. So there is no, I have 8. It was 8 already.
It was 9. It was correct.
It was correct. But I did not count. It was by accident. It was correct. Was it? So we make a 4G one. We think this example G is 2. So I make an axon, and I can insist that many properties are true. So what are the properties? The properties, later we need slightly more than 4G1, but this is as a story. The properties are that the polygon is convex. So what is not good? This is not good. This is the polygon is not convex. I can insist that this resulting is convex. I can insist that lengths are the same. That this length is the same as this. And that this length is the same as this. And that this length is the same as this length. And that this length is the same as this length. In the geometry, there are much more polygons than in Euclidean geometry. But there is also a constraint about the angles. The sum of the angles, let's say alpha 1, alpha 2, and so on. The sum of the angles is root pi. In Euclidean geometry, if you take a polygon with 4 sides, sum of angles is already 2 pi. If you make a 5-gon, the sum of angles is more than 2 pi. In Euclidean geometry, when I have a 4-gon, I can split it into 2 triangles. This gives me sum of angles pi, this gives sum of angles pi. So sum of angles, if you have a 4-gon, sum of angles is 2 pi. A 5-gon, it will be more. But in hyperbolic geometry, I can do this. So what we do now is, we do the identification which we did yesterday. I say this thing, I glue to this thing. This I glue to this. This to this, this to this. Now we look what happens. This sector appears somewhere. But every sector, all points get identified. So all corners get, this point becomes the same as this point by this identification. This goes to this. So this point becomes the same. Then I do this identification. So this point becomes the same as this point. Here then we continue. This point, where it goes? This point goes to this point. Finally, at the end, I have only one point. So what we have is, after gluing this, at one point I see all the sectors. I do not know in which order, but I see all the sectors. Alpha i's appear. And the sum of the alpha i's is 2 pi. That makes for me a perfect manifold where the sum of the angles around the point is 2 pi. So this makes for me a Riemannian manifold. But because we had here because this is part of the complex plane. So here we have our J operator. If I have a vector u, I know what is J u. I have to turn this vector by 90 degrees. Complex people say multiply by I. So when I do this doing, the J operator remains and I get a Riemann surface. Uniformization theorem says the following. If you have a Riemann surface of genus G or bigger, so you have a surface with the J operator, you can always find somewhere else a polygon, not for G1, slightly more, I will tell you later why. You can find a polygon with the possible and an identification scheme such that your Riemann surface that you had from the very beginning is as Riemann surface isomorphic to the one we constructed in this geometric piece. This is called uniformization theorem. You remember the red line from yesterday? Yesterday we had the surface of genus 2. I have drawn the A curves, the B curves. Then we had this point, and this was connected by the red line. When I cut along the A and B lines, this leads to a 4G cone. But if the genus is higher, there will also be red lines. Here I have the same thing. And what I do is I connect by a red line. So there will be G minus 1 red lines. So when I cut the polygon which appears, has how many sides? It has 4 G sides. Coming from cutting along A and B. And then I have 2G, G minus 1 red lines. I cut along. That makes it a polygon sides plus 2G minus 1 sides. So the polygon which appears is not a 4G gon, but it is a so much gon. It is a 6G minus 2 gon. You draw a 6G minus 2 gon with identification. So what happens in the picture is it could be that this gon does not exist, but that here we have the red line, and the same red line appears here. And then the identification scheme is this, becomes identified as this. And those red lines appear G minus 1 times, but when you cut, the number of sides doubles. So the identification scheme is slightly more complicated than the one we have. So the uniformization theorem says there are enough polygons to model every Riemann surface. There are enough geometric polygons with constraint sum of angles 2 pi, lengths which we want to identify equal. There are enough such angles, convex, there are enough such polygons to make every Riemann surface of that genus. That is uniformization theorem. The theorem was claimed several times. Poincaré had an idea of proof. The proof looked good, but then Brouwer found mistakes. Then Goethe made a proof. Then there are difficult proofs. But I think in my notes there is a straightforward geometric proof, which I cannot tell in details here, it becomes too long. But in the pages you have is a proof of the uniformization theorem. So, uniformization theorem, we need this hyperbolic geometry to make many polygons. Of course, the model of hyperbolic geometry by polynomials is not needed. You can also look in the textbooks or other models. But I like this because it comes right away out of secondary school. Secondary school, people study polynomials of degree 2 at least during 1 year. So in fact what they are doing in hyperbolic geometry did already. I don't think it's a good idea to tell them too early this. But I think it's a good idea that the teachers know that they know how to do geometry. So this is improvisations here. And unfortunately, I cannot give this in details. So what we can do is, in order to see what happens, we can try to count how much degrees of freedom we have in making such polygons. So now we do something. We say what is the Riemann surface, the decorated Riemann surface. Decorated Riemann surface. What is this? First, it is the surface, always oriented compact of some genus. Then we have this J operator, and the decoration is cutting the surface with curves like above. So you put enough glasses in your surface, AB curves, and then you connect them explicitly by red lines. And this cutting is the decoration. So, decoration. So decoration can also be seen as breaking symmetry. If you draw on some round object, you draw something, you break symmetry. In billiard, everybody knows this. On one of the white balls, you draw a small dot, then you know which ball is yours. And you break symmetry. So that's our decorated Riemann surfaces. And now you can take the space. You can take the space of all decorated Riemann surfaces of some genus, of some fixed genus. Genus for what we're doing is should be bigger equal than 2. So your objects are decorated Riemann surfaces of that genus. And now you can ask, is there a natural way of measuring distance between two Riemann surfaces? Also is yes. I will say there are many natural ways, so that contradicts the word natural. If you say something is natural, that means you exclude all other guys, they are less natural. Here you have some possibilities. So this becomes again space. And you could say, this is probably a very complicated space. Theorem of Dracula says this space, as topological space, is isomorphic to the real space to the dimension 6G minus 6. So Riemann said something in this sense. He did not have the space, but he says depends on 6G minus 6 parameters. This is something which is sometimes confusing. Some people, they do not have the space, but they say the dimension of that collection is, and then this dimension is way of thinking the number of parameters you need to do this. But you must be careful. If you have your number of parameters, then there's a big difference between thinking this and saying it is this space. If you do this, that means you can choose your parameters freely and they exist exactly one object. Let's do Euclidean triangles. How many Euclidean triangles you have? Let's label the decoration is you number the vertices, the corners. Then you have 3 numbers A, B, C. But those three numbers, they satisfy a condition. A will be smaller than B plus C and so on. So the space of Euclidean triangles depends on three parameters, but not every choice of parameters corresponds to a triangle. Here, this statement, we say more. Every choice of the parameters corresponds to exactly one Riemann surface. Perhaps I can draw for you where are the parameters. So, for us, the Riemann surface was a surface with J operator. This polygon story tells we can upgrade the geometry in such a way that we have a metric. And the metric of hyperbolic plane is very special. The curvature of that metric is the Gaussian curvature is constant -1. So what I wish to do is I wish to add a creature here, which is of analytic nature, and such that surface J and this new creature makes a metric. So what we do is we take a triple surface, J operator, and volume term. So omega is an element of two differential form on the surface, and omega is positive. This positive means omega of two vectors, u and j of u, is positive. For u and that vector, which is non-zero. Positive in this sense. So, the nice thing is, this expression is a metric. This, you can say, this is the length of u squared in the geometry J omega. So uniformization becomes equivalent to say, to produce a volume form such that the curvature of that metric, that's a Riemann metric, such that the curvature of that metric is -1. Also in the notes is explained how to find this omega. So we have here a Riemann manifold of curvature -1. And in this, because we have a metric, it is easy to tell you what are the measurements. So, I have drawn for you the surface with a lot of curves on it there. I wish to make parameters. I wish to make numbers. So here was the curve A1. And now we have a Riemann metric. And this Riemann metric has negative curvature. Then differential geometry tells us you can deform this curve to a new position, such that in the new position you have minimal length. So, the parameters or lengths of curves, but not exactly the curve I have drawn. The parameters here, the 6j minus 6, are obtained by first choosing a metric, hyperbolic metric, choosing well as omega. Choosing this omega goes by minimizing the project. So perhaps, I do not know, the Gauss-Bonnet is 0. Everybody knows Gauss-Bonnet is 0. You know what is Gaussian curvature? Huh? Yes. So Gauss-Bonnet theorem, Gauss-Bonnet theorem tells you, if you take the Gaussian curvature and you do integration with respect to the Riemannian volume over the surface, then you get a number which has topological meaning. This is 2 pi times the Euler characteristic of the surface. What is also true So the Gaussian curvature, geometrically something easy, algebraically something complicated. We have heard in the lectures that there is a Riemann curvature tensor. Riemann curvature tensor is a two-form with values in the endomorphism. But those endomorphisms are special. They have a square root. The square root is called Pfaffian. So the Gaussian curvature is Pfaffian. So I do not wish to do this linear algebra. The Gaussian curvature is something I can extract in an algebraic way. So this is the square root. So therefore it is natural to look what is the integral of k squared. The same. And amazingly, this integral for every metric is bigger or equal than 2 pi Euler characteristic. But Euler characteristic tends to be negative, so it's the absolute value of Euler characteristic. And finding this best omega is the same as minimizing this quantity. Minimizing a geometric quantity goes by a gradient method. Difficulty is always to see that this process converges, that conversion to something reasonable. So that's the difficulty. But that's the idea. You take any metric, you minimize it. So call energy of such an omega, this integral. And then you minimize energy. This goes to uniform multiple surface. I do not know how much time.
For the moment, miniature one.
How many minutes?
15 minutes. We have an obsession.
How many minutes?
10 minutes for 10.
10 minutes. So when I multiply by 2 means 20 minutes.
We have the obsession and
so I multiply by 1.5.
You can follow if you want after the way.
No. I wish that you see the 6g minus 6 lengths. That here we say the Riemann surface, perhaps you don't know what it is. It is the surface with the shape. Then whatever is the shape, choose an optimal omega, making curvature minus 1. Then we have a Riemannian method. And in that Riemannian method we can measure the lengths of curves. So I wish to make 6g minus 6 numbers. So I must in principle produce 6g minus 6 curves and say these are the lengths. But this cannot be true. Because the real numbers can be negative, so it cannot only be lengths. First thing. The truth is, I produce 9g minus 6, 9g minus 9 curves, and then we have all those lengths, and out of those lengths, we cook 6g minus 6 numbers. So we do this. So we have seen that we can build a surface with those T pieces. Every surface we can build T pieces. And the number of such T pieces was related to the Euler characteristic. Was minus Euler characteristic. So the number of T pieces is minus the Euler characteristic. This is the same as 2g minus 2. If you draw so many T pieces on your surface and glue together, how many boundary curves do we have? The number of boundary curves we have is 3 times 2g minus 2. If we could count the boundary curves of the T pieces, but if we could, here is another T piece. So So this curve in this computation will be counted twice. So the number of curves is this. If you cut in T pieces, the number of curves is this. So let's compute this. That is 6g minus 6. This is 3g minus 3. But this is very good. That's half of what we're aiming for. So now, it could happen that we have two T pieces which are looped. So when you have this, you can make a new curve. New curve. And what we can do is, this new curve, I can make it in many ways. I draw this curve which is dual to this cutting curve, but there are many ways. What we can also do, instead of going simple like this, I make first a twist. So here I have my T piece, and then I can say here I am before. So we went from here, we went up. And then we went and came back to there. What we can do before going up, I can walk in this tiny piece of cylinder and go there. And then go up and come back here. And then do the same rotation to go there. So I twist some bottles of wine. They have glass, and all bottle of glass, but then to make the bottle nicer, the lines of the glass are twisted. The Muscat de Frontignan is like this. This is a city near the university where I studied, therefore I know this. So you twist this, but you can also do this if you take this and you then vertical lines, they are wrapped around once. So that means we have here we have a cutting curve C, and the number of them goes to 3g minus 3. Then we have the first dual curve, d1 going to d3g minus 3. The first dual curve, that is this one. But then we have to twist the dual curve. That makes t1 to t3g minus 3. So now I have 9g minus 9 curves. So all those curves have lengths. So for those lengths, I take the log of the length of such a curve. That makes a real number which can be positive and negative. The length is positive. If I take the log, I get the real number. If the length is more than 1, the real number is positive, and if the length is less than 1, the real number is negative. This kind of numbers runs over whole real numbers. And for the other, I do the following. I take the length of di minus the length of di. That makes other numbers. This is a positive number minus another positive number makes a number. You do not know if it is positive. It could be that the dual curves are short and those are large. It could be that those are short and the dual long. So this makes another system of real numbers. So here we have 3g minus 3 of them, and we have also 3g minus 3 of those distances. That are exactly the parameters which parameterize the 6g minus 6. These are mathematicians. But then come physicists. Physicists, they say our universe has a simple model, they make a lot of computation. Other physicists say, first we look for mathematical space as complicated as possible, and then physics uses that space. So this is extreme. So this space is very good if you wish to study evolution of surfaces. A surface is a generalization of a graph. A So if you have a graph, the basic operation is you contract this and split it in the other way. But then you have in the middle a point where you have a point where 4x will go away. This picture, the surface is much nicer. And now this tube I glide along this and stays over the surface. I do not have intermediate point where the combinatoric changes, so it's much more homogeneous. So this is of course appealing for physics, and this is the basis of string theory. It's beautiful mathematics, and from the physical people I heard negative news about string theory. What I heard, I do not understand physical interpretation, but the mathematics of this is beautiful. And it's a pity that nature does not use this mathematics. Thank you very much for that.
So, thank you very much. We must go to the lab because we have the session with the software of okay? So, yesterday we confirmed that he will come and I hope to find him there. Okay.